that review during that collaboration phase before it gets to engineering design release to construction. Following on from that, I just wanted to pick up on a couple of the examples that we use for planning. So it's not all about the design and the permanent works. We do use digital tools for the construction phase, and we do use them in temporary works and in kind of the planning of the works to include that interface with temporary works, where we get a lot of safety risks and again quality risks. So there's an impact that if we don't get that right, there's a real risk that we won't then achieve the quality of the finish that we need to achieve to be able to hand over ultimately. And staying on the theme of planning, one of the real fantastic features of having lots of these digital tools is that is how maneuverable it is to go from something small scale to something big scale. So you can look at the site wide and look at some of the bigger interfaces, and you can take out some big statistics. And then when you need to, you can then go into a small platform. So, for example, these are the poor models. And there is a model that's produced by BYLOR. They represent the construction sequence, and they're all ordered. They're in order of how we're going to pour them per building. But then you can, when you look at it as a big picture, you can also unpick. So that's, for example, the inner HR. And this one here in the middle is just one level of HR. And you can just turn those on and off very quickly to see if you need to understand a bit more of this sequence, or if you need to look at an interface between this level and another level. And it just gives you that, I guess, that option to be flexible with what information you look at and how you hone in on different details. And that's very different from having a set of drawings that only describe one section of scope. Being able to overlay information and be able to extract information in a different way is really powerful. And given the complexity and the size of the project, we would struggle to do it in a different way. I guess what I could have said again within the planning phase and the poor models is actually the poor models also underpin our program. So how we use every poor model that we produce has a poor ID, and those poor IDs then feed into a program. So then we can report in 4D, and we can produce those plans. And that also then leads on to procurement. So we can then use that assignment of the poor ID, we apply it to the reinforcement, and then we can pick off the amount of reinforcement that's allocated to that poor, and we can call it off. So we're starting to really connect all the dots now through the initial design interface stage, where we're looking at this reinforcement, to applying it with the planning information, to then the extraction in the procurement phase. And then going through to construction, we've seen this picture. But we use the models on site, and I'm sure everyone who's on site will see. We use them for checking the reinforcement, and we use tools such as this here, which is a BIM collab, to raise issues and to highlight different bits and to assign embedded plates, etc., and voids. And really, it's all part of the suite of tools that the site engineers have to process all of this information that they're being bombarded with at the time. And I probably, and then leading on to post-construction, we still use digital tools, so we still use laser scanning to pick up that data at the end that will then feeds into our completions. That's possibly a bit complicated, but that's me. We have one of the things, I guess, that underpins the whole process is how we communicate and the formats in which we communicate. For us on the project, we use IFC, which is just like a PDF of the model world, and that allows us to share information back and forth. And I just think it's interesting as we move forward with the way we work, then it's important that we establish these cornerstones of communication when we go forward. It's something we share, and again, tying into the whole process, so through tender, design, collaboration, planning, procurement, construction, post-construction. One of the benefits of using these tools is that they are digital and there is data there, so we can extract this data to do reporting at different stages, and that obviously with sufficient validation of that data, we're in a position where we can start getting some really high value reporting as close to the field.
So with the design and everything, you were talking about the rebar and so forth, and the different layers of the concrete. When the embedment plates and things go in, do you also design that in to your model? Does that come at that stage?
It does, yeah. So the designer, so as BYLOR isn't involved in the design, but we do review the design, and the plates are all declashed during the design phase. The challenge is that there is some movement, there's some rejigging afterwards, but there are, but ultimately, yes, we do receive a declashed design from the designer. I guess there's some in theory we receive a model that is declashed, but that declashed model does have tolerances on it, and we're also instructed the ideal location, so there's a bit of give and take between that. I'm not sure I answered your question, but it's close to the truth. Thank you.
You talked about poor models there. It needs to be poor models. So you could take any sort of building in the whole area and say, from that building from the bottom to the top, this is the sequence of poor models. So you can have a list of 1 to 10, and you're going to be pouring in those sort of. So that must help you with your organising your completions, really, doesn't it?
Yes. So we have I guess during the initial phase, it's built. So during the design collaboration, the pour models are a tool to help us communicate our construction sequence. As we get closer to the construction, sometimes there'll be give and take with the planning team that maybe kind of pour what used to be pour 1 is now going to be poured second, and pour 2 is now going to be poured first. But yes,
generally you can see that.
Generally you can see that intention. And I mean that's the plan. So the project controls have in a P6 program, they have all of the core IDs included. So we can just take that data as a source of truth and map it against this to show the progress.
With the laser scanning that you touched on again, what's the scope requirement? And what's the intention for?
So I might pass it over to
how much you're going to use it?
Yeah.
So it's actually a hot topic at the moment. For us, it does 2 jobs. One, it's a way of verifying that we've complied with the tolerances. But then the other piece is it provides as-built information, and that as-built information is given to MEH as an input. So for the follow-on works, to know what they're getting. And there's some discussions at the moment about how best to work together with that information. But certainly we've found it's a great way of, as long as you can have a nice clear area, then you can gather the information really quickly, and then you get to sit, rather than in the middle of the works, sit in an office and process that and analyse it and have that information good to go.
And it's pretty quick, isn't it?
It is. There's still definitely, we've been on quite a learning journey, and there's still some more learning to do. And there's some discussions at the moment about certain types of tolerance you can deal with really efficiently with the laser scanning. Certain types of tolerance still need quite a lot of manual work. So we're actually rethinking what are the best tolerances to be working with that will help us to work efficiently.
Also, it's fast on the field, but it does require processing time. So my point is no silver bullet to these things.
Is it got inbuilt like smart identification with it as well? So that you in the display that you showed on the screen, it highlighted the embedment. So I assume it can go. That's a square.
It identifies things like plates. Yeah, so we've worked together with the software developer for the scanning system to develop that. So it identifies the plates, I think, effectively automatically. Some of the other types of embedments need more manual work, but you get a point cloud, and it takes photos as well as the point cloud, so it looks visually like a 3D room to work from. And obviously you can slice drawings from it.
Okay. May I have just one quick question, and that is regarding BIM. So the last time we built a nuclear power station in the UK was way before any kind of digitalisation. So have you got any metrics on how BIM 3D, 4D and 5D have saved time, money, effort? Is there any kind of figures on that at all that you may have?
We've got lots of specific anecdotes, but it's probably an exercise that we could do with pulling them together as a narrative.
I guess it's so long ago that the reality is the design of what we're building, and I think probably, if we're honest, some of the quality standards of what we're building have changed quite a lot in the same time. There's probably a lot of different factors involved. As Frankie says, there are anecdotes, and I guess the obvious one is that those photos at the beginning, like for like, so when we first started, we took a little bit of Flamanville, a tiny bit of Flamanville from the Flamanville drawings, and we tried to build it, and it was a disaster. Stuff didn't fit. And we then remodeled it and did it again. And I forget the percentages, but so based on that little tiny example, there was a huge percentage benefit, both in terms of the programme, but also in terms of being able to reliably get what you want.
Thank you. There's a brief hand. Mike, do you have something to ask?
Yeah, I was just going to remind really that it's always worth working, hearing radio to chat stuff working for anybody. You know, specifications don't really work for us, and stuff are always challenged. It helps.
I think we're probably agree.
Yeah.
We're going to agree, yes.
Thank you, Mike.
The only point is that a lot of this IT requires internet access, etc. And we're certainly having a problem down there in the bowels and stuff, being able to link into the app to download it before you go into places. And it's going to save us a lot of time if we can actually get live data as where we are. Any thoughts around that?
So it is a challenge, and it does rule out quite a lot of kind of options on the market around having apps and stuff. It means we are committed to basically having particular suppliers that provide us offline apps that then sync automatically. So we can't always have access in the field live, but the minute you come into Signal, it will update. It will update and it will sync. So it does limit what's out there on the market at the moment. Especially there's a huge amount of investment. And you can see it's quite a lot of competition, but yeah, not everyone delivers the full package yet.
We've got project services who are looking to install some Wi-Fi in and around the plant. They've got the next Tuesday to have a look and see what they can do with the galleries. So yeah, they are thinking about it, but that's at ND side.
Some of those joint preparations.
Yeah. Our strategy has been to choose systems that don't rely on it, because we kind of figured that whatever you do, there'll always be a corner somewhere.
Yeah. And the more you get, the more you're built in as well. Like you just have to have repeaters everywhere.
Hey.
Good evening, everyone. My name's Will Peach. I started on the project back in 2014.
Wow.
With a few faces. Still building that trial building you mentioned. A few things have changed since then. Not least of all that we have one crane, 80-ton crawler crane with telescopic jib. We've moved on since then. We're currently sat at 54 tower cranes, one with a dedicated training school. We've got over 16 crawler cranes, ranging from 80 tons to about 300 ton. 4 gantry cranes, 4 mobile cranes permanently on site. Oh, it jumped down.
Very laggy.
Very laggy indeed, I only pressed it once. And of course, we've got Big Carl. Yeah, we all like Big Carl. We've got some photographs in a bit, don't worry. But that's not all the lifting equipment we have to deal with. We've got everything else that lifts the thing off the ground. So there's a few photographs there, I won't go through it, but pretty much the only thing that we don't have to worry about in the lifting world are turfers and pallet trucks. Everything else, one way or another, comes past the lifting team. So there's an awful lot of work that needs to go on in the background before we get. That's all right. Go back. Before we get into any of those big car lifts we've got in the middle there. So HBCE, massive site. We can't have a normal setup with the workforce. It just wouldn't work. That slide's basically just, it's an example. You know, you've got a lifting team on area A. They work with a construction team. They work side by side, as you would have probably on any construction site. Difference is here we've got 10 sets of that. which makes it, a company in its own right. A company would have a support team. Because we're so large, we have that on HPC. We have a central lifting team. I'll fall out with this clicker in a minute. Not over here. We have a central lifting team who will perform that function of a company central office. But we've got that on site just because of the sheer size, sheer complexity of the lifting we have to do at HPC. More so than on other jobs as well, the clarity on the inductions, assessment, training of the people we get in. We've got a lifting school, I mentioned that. So we can train people up ourselves. People that are coming in through the door, we can make sure they're at the right level, the right competency level. We're not sure, we can back up to the school to be assessed. We've got simulators up there, we've got operators. So we can, again, refresh train them. They've got lots of types of crane. They can make some models so we can send them up there just to get them a bit more comfortable in the seats, make sure they're happy. Roles and responsibilities. We need to know who's doing what. It's massively important. It might seem obvious, but in a lot of the construction outside of HPC, that wouldn't be so definite. But here, absolutely clear on what your roles and responsibilities are, who you report to. And appointments. Again, outside of HPC, appointments are something that should happen, absolutely. Legislation says you should appoint people. But here we're absolutely clear on appointments, so you know who you're reporting. We can do the checks on everybody to make sure we know who we've got doing the jobs for us, so we can make sure they're the right people. So, why does a load need to be validated? Well, lifting a load, says there, put stress on a load it isn't designed for, like jacking a car from a bumper. Yeah. So we're talking about nuclear safety. We don't want to be lifting something that we think is okay, but we might put some stresses into it, which you can't see with the physical eye. That gets put into some concrete, and then we've got a latent error. So it's absolutely imperative that all the loads that we lift are validated. So to help us with this, we break them down a little bit. Manufactured, bundled and assembled loads. So for manufactured loads, we've also got the supplier, supplies with certification, provides us with lifting points, tells us where they are, what they are. But that's broken down again into containment, so skips, things like that. The test and inspection engineer can come and check these, make sure they're colour coded. Materials. Oh, I did have the HG tank on there, you see? Such a good photograph. So these bits of kit are produced by a manufacturer, but they are CE marked, got design drawings for them, marked lifting points, methods drawings are produced, that's handed to us. As an engineer has thoroughly thought about this, we lift how we're told to lift it. Plant, again, doesn't always, but should come with marked lifting points. Seems obvious, little sign on a hook, you lift there. So often though, you get lash down points, tie down points, little loops that are for something else. We need to make sure these things are absolutely needed for lifting. Bundled loads. Again, it might seem obvious. I mean, scaffold tube, but rebar, you often need that, but you've got lifting points the right distance apart. Is there a bend in it? Pipes, sequence of pipes, we're lifting those. We want to make sure they haven't got too much of a span at the end. They get, there's rules, there's things that are in the spec that we need to follow. So again, make sure it's validated. And then assembled loads. So assembled loads are checked by a temporary works supervisor, temporary works coordinator. It's on a register somewhere. It'll be designed. Detailed, a couple of examples there, rebar cages, they're all assembled, things put together, cantilever platform, but any formwork or shuttering is assembled. So we need to make sure that whoever's put that together is being put together correctly, and it's signed off by the person who knows about it, the person who put it together. They're the ones with the drawing, they're the ones with the control, so they need to tag it for us, so they know it's right. And we've got other assembled loads. There we go. New points of photographs there. So I like the one on the left. It's not often you see that. A crane lifting a crane. Yeah, that's when we had to lift out 1C1 from the centre of the nuclear island so that we could get the next ring on. So it just got casually lifted off by Big Carl, placed on the ground. So we could put a ring on and he was lifted back in a day later. Yeah, so to Big Carl, it's nothing. I think it's 130 tonne easy peasy. Dome lift was done very recently. I mean, just in the dome lift, I think that was 130, but even the hook block is 56 tons. The Novum beam is 70 tons. You know, all this massive weights we're talking there. And I think that the precast there on the right, I think that one was about 580, I think, tons, which is still not the largest we have lifted or will lift. But all assembled loads, obviously the amount of checking that goes into any of those, a lot more things to check. But to us, we get handed over an item that's been checked. We've got a certificate, we get told where to put our lifting points, and we dutifully follow that information, at the right lifting points, the right accessories to the right lifting points so that we can lift it safely. Part of what we do, even with assembled loads, we have to check them. Photographs there can assure you weren't ready to be lifted. It's not what we found, but this is just an example of what goes on site. You know, rebar cage with loose rebar or a bit of scaffold tube in it. You just go around any construction site and you'll see things like that, work in progress. But all too easy for that sort of thing to be left in there. So we need to make sure we check things. The one on the right, yeah, that was bottle of water. Hot day, somebody slipped it in there. Again, whose job is to check that? You know, yes, the load will be tagged to say that it's assembled, but we need to make sure that everything we do is checked before we lift it and it falls out. So if you're on site, don't leave your water bottles and shutters because it just adds a little job for our guys to do.
Even Mars bar members now.
We'll definitely find it then. There we go.
Just enough paperwork.
Yes. Yeah, so we talked about sort of firsts and leading the way at HPC. Might seem obvious, but when you're lifting a cage, you use tie wire. Yeah, that's what everyone else uses. And tie wires, yeah, not that great as a structural element when you want to lift something. So the team did a lot of work. Welds, the next thing, you will see that on quite a few sites. For lifting, designated points, welds, lovely, 10 times stronger. The clamps, that's the first site I've ever been on when people have actually thought about the idea about using clamps. A lot of work went into where they go and what they should, when they was right in the wrong place to use them. But it's brilliant, so much stronger, really identifiable as well from a lifting point of view. If we know there should be some clamps on a rebar cage before we lift it, that's really the spot. You try and spot welds, whether or not they should be there. It's a lot easier to miss a weld than it is a clamp. So really good stuff and really strong. When these things are being chosen, again, by the designers, by temporary works teams, things like rotating of cages, where the lifting points are, these are all things that have to be considered to make sure they go in the right place, the right numbers are used. It's not just made up on the spot. We have to consider the bending and turning in transit. And I mentioned all these things get validated, and this is what we get as a lifting team from the temporary works team. Is tags. Now on BYLOR we use C&M tags. Pretty much do the same thing. One is gives you a little bit more time. It's a little bit for a rebar cage, say, but if you're rotating a load, something needs a briefing, very specific way of doing something for a design, then we M tag it. The temporary works guys know what they're doing. We know what we're looking for. We won't lift it without one of those on it. And on that, it's got who's signed it off, say it's okay for lifting, the date, how long the tag's valid for, any relevant information about the drawing, so we can go back and just double check the lifting points, and any other useful information for it.
Sorry, what's that C tag there?
Oh, C tag, that's literally, so C tag is, so C&M are just names we came up with. They were, I think, in the annuals at the time, it's just a thing.
I can't remember now. I think C is mandatory. Yeah, C is common.
Yeah,
that means mandatory briefing.
Mandatory briefing. There you see. There we go. So, yeah,
before you make the lift.
Yeah, before we make the lift, absolutely. So we wouldn't touch it until that's on it. So of course, as soon as it's landed, that comes off. The moment it's landed, something is going to change. That comes off because you loosen one nut, loosen one bolt, and suddenly that whole dynamic's changed again, and it will need re-inspect and re-tagging. That's why the date's on there. So it's a very finite kind of period. Just lifting the load safely. So going into the nitty gritty now. So a lot of you guys are on site here. I'm sure the guys on the online are familiar with construction sites. But we need to make sure when we're lifting that we've got space to control the load safely. We need to make sure we've got clear walkways, clear accesses. Part of the training we do, but also when you guys are out on site, just make sure you're, it's always helpful. The more people know how to look after themselves, the better it is for everybody. No crush zones. As buildings, as these rooms more and more go up, space gets less and less. Crush zones naturally increase in number. We're going to be more and more mindful that we're lifting things into areas we can get out of, that we're not getting ourselves stuck in a corner. Equally, when we're looking up into the sky, we've got more and more things up in the sky, not least of all tower cranes, concrete pumps, scaffolding, and the structure itself, of course. So we need to make sure that when we're lifting things around site, we're looking out for those. So we don't hit them, don't damage them. And the simple one, space for rotating loads. This is actually one people just don't really think about. You're lifting and tilting a load. People often say, well, I won't walk underneath the bit where it can drop back down and squash me. Yeah. But what about where it slides? Yeah. Now, the load's done properly. It'll have chocks, it'll have blocks, it'll be lifted up in such a way it can't happen. But you never put yourself in that situation. You always make sure you're out of it. You always plan for the worst, and then we can only have a good outcome. And again, not the most exciting innovation you ever see, but things like tagline retrievers, push-pull sticks. Keep yourself away from that load. Hinkley, as other sites, we are a safe site. But with the number of lifts we're doing, we're over 60,000 lifts a month, which is absolutely unprecedented on any other site in the UK, possibly the world. Things do go awry, so we have to put into place things to help people not go underneath the load. So tagline retrievers, so you don't have to get too close to it, you can pull the tagline towards you. Also, when you're over edges, you're not reaching for it, it's towards you. And the push-pull stick, of course, to keep those little precious digits away from any of the loads.
So do you have a no-touch policy or something like that?
Sorry?
Do you have a no-touch policy?
Interesting point, no, because actually a lot of the time we do need to get in on the load, but it's no touch policy above shoulder height. That's the easy one. So that's definitely a number of times, and it still happens because people, they want to do the right thing, they want to do the job. They're reaching up here. Nobody can control a load when you've got a hand up in the sky. But we are looking, we're investigating with pushing more into push-pull sticks.
So that's the column place at the moment. It's coming in.
It's coming in, correct. Yeah, absolutely. Yeah. So if we went to K11 into the rebar yard. Yeah, exactly. Yeah. So the rebar yard on site where you've got we've got more space, level field than actually they're used. On site, of course, these push-pull sticks, they stand 6 foot plus high. And when you're walking up and down, in and out Nuclear Island, and you've got little staircases up and down, and you've got to go, they're maybe not the most practical use. So we use them where we can, but we have to be realistic about this. Are you going to carry a 6 foot fiberglass pole around everywhere we go on site? So we're realistic about the problem. Equally, we need to build in the training, like how to manage a tagline. It seems obvious, but for the practical, the engineers amongst us, you can try controlling a load when you're straight below it. That bit of rope doesn't do anything. It's much easier when you're in a straight line with it. It's all about training and understanding how it should be done. So that's actually an extract from one of the Slinger's guides.
You do get extendable push pulls, don't you?
You do, although we have trialled them. We've done quite a lot on this. It was probably a couple of years ago we trialled the extendable ones, and they when they work better at pushing than pulling, shall we say. And the problem then is you've then got a loose item. So not without, there's, absolutely there are. I mean, the tagline retrievers are a little simple thing they sit on your belt, that long, really lightweight bit of kit. But the extendable push pulls we did have not the most smooth trial with when we did them. But again, we're developing, depending on what team you've got, that's with a lot of the places, this sort of thing, it can sort of come in waves. What doesn't work for that team might work for another team. So we keep on trying to make it right and work for the teams we've got and the experience and the competencies of the guys we've got. And then lastly, really, a bit of crane coordination. Oh, the video's playing at the click, never mind. So we've got, I think we call the Master Airspace Plan, the MAPS. That's created in conjunction with the principal contractor. It's their responsibility to look after coordination on the site. So we input to that, but we use that for our crane coordination. It's in the middle, you can see the video playing there. That's just all the cranes going up by date. So I'll keep on talking over it. We've got 3D modelling. Things like Francesca's team will help produce those for us as required for each platform as they're needed. The out of service crane code is very important. All these cranes, as you see from the map, there's so many of them that when they're operating, we've got systems in place, namely AMCS, which is an anti-collision system, stop them hitting each other. Of course, you pot them up at night, then what stops them hitting each other? So they get parked out of service, they get parked in a particular position, and they weather vane. So they don't turn around, they go against the wind, they're going to fall over. So they have to spin in cone shapes like you can see in the bottom right-hand corner there, or discs if they're a flat top. They always stay the same radius. So we have to do a model like that to check that any new cranes, this particular model was done years ago as we started HPC, but we have new cranes coming in, couple in the last year, in fact. Brand new ones we weren't considered. We have to make sure that they're not going to clash when winds blow and it's at night time and there's no operator that can control them. And then the last sort of planning we do is just load path planning. So when you've got a big car and he's lifting a 300 ton ring lift and he's going over that crane, around the side of that crane, in between two other cranes, you have to make sure the load path's right, make sure that you're not going to clash with any of those other little cranes, not going to damage big cars, but you usually don't want to knock a crane over so they don't play skittles. So we make sure the load path's absolutely planned so that we can get the load exactly where it needs to be safely. So that's me on cranes. Any queries or questions?
I had a little one, just a little one. You talked a lot about planning the load and planning the lift. How do you plan where you're putting the stuff? Not the rebar cages, but maybe the rebar or materials you're putting into areas. How do you know where you're putting it as a safe area to put it?
That's very, so there's a element of work that's actually going on now a bit more. Generally, until very recently, it's been on a grade platform of concrete, foundation. There's not really too much of a problem with that. There's space you can put on. Of course, as we start coming up out of the ground, then slabs are becoming suspended and there's a lot more working platform, but becoming a lot more critical. So those elements need to be, well, basically temporary works again, are tagged up to make sure that this is a loading area suitable for this bit of kit. I mean, not so much actually rebar and shutters, it's things like the mutes, the scissor lifts, things like that, that really take more attention because they're quite a lump in quite a small area with quite large point loadings. So absolutely it needs to be
I was keen on the, you talk about don't pin yourself in.
Yeah.
And then we could not pin ourselves out of walkways if we're using walkways for other reasons. That's sort of, I'll be quite interested in seeing how you're managing that process.
Yeah, it's as with back to the original planning. This is what I'll get our gel free card on this one. That the lifting team work hand in hand with the construction teams because we don't lift anything. So we're just been told to. Ditto, we can't lift it anywhere unless we're told to put it somewhere. But absolutely, it's a thing. We can't just go and put things where we want to. So it has to absolutely be planned because they lose walkways, there's scaffold, decking over large voids, staircases, other things. So yeah, we have to be very mindful, even more so as we're coming out of the ground.
You answered some of the questions I was going to ask there, but do you envisage as the build gets more complex, space is going to be tighter, different components will have to be thread in rather than just lifted down? So topping and tailing, tandem lifts, transfer of loads.
Yeah, so we don't envision too much topping and tailing with the cranes we've got on the outside, but you're absolutely right. When it comes to getting things into the buildings, then we're going to have a lot more of that smaller lot we looked at there.
Yeah.
A lot more rigging.
Yeah.
A lot more fleeting of loads. And that's a whole piece of work that's going on at the moment, because that's, yeah, you're absolutely right. I mean, 54 tower cranes, the team we've got at the moment are, they are world experts. When it comes to multi-tower crane sites, you'll struggle to go anywhere and find a more competent team when it comes to that. But as we get more and more boxed in, and we have to bring the right teams in to really manage that fleeting of bits of kit. And the MEH guys are very much on that. They've obviously got their own lifting teams. We end up lifting a lot of their kit somewhere next to a doorway, and they thank you very much, sign off there, and we'll very heavily walk away as they then get all their fleeting kits out and then try and manoeuvre it where it needs to go. We've got a lot of temporary running rails going up in buildings. So a lot of those plates you saw in the digital earlier, we're getting running beams welded, bolted to those, so that we can temporary gantry crane, so we can lift things inside buildings.
Transfers.
Absolutely, yeah, with interesting little cantilever beams to get steel plates in. So yeah, there's a lot of that as well going on inside the building, away from all the dramatic crane pictures that we see.
It's very interesting because I work with the storage and transport on the AD site, and we're working with the final mile right now. So we're bringing up the kit to where you'll just lift it off the vehicles possibly and place it for the MEH.
Yeah.
And then they'll take it into their building. Yeah. So we all fit together as we said, like a jigsaw puzzle. And it all
is that.
planning, that everything.
Huge amount.
Then the wind comes along.
Yeah, I know. And we apologise for the weather. Yes, it means we can't lift for anybody. So yeah, that's one thing that the MEH guys won't suffer with when they're inside the building. It is lifting, but we do suffer with the weather, unfortunately.
Yeah, but the team's great to work with.
That's very
Thank
clear.
you.
Yeah.
With all these interfaces, they're coming thick and fast and only increasing going forward. Is there any kind of natural sort of discussions that would happen for this team becoming evolving into the HPC lifting team?
I think the right way to manage it going forward is definitely a discussion to guys, yes. And then there are discussions ongoing about how people can work together most effectively.
Yeah. Interesting times. Yeah. Yep, lovely, thank you.
And then wait 10 seconds.
Right one, perfect. So, hi everyone, I'm Bewinder. I first came to the site in 2018 as a site engineer. I then worked my way up through section engineer, where I was on the Unit 1 on the outfall building, which I'll be talking about shortly. I'm now in a materials engineering role, but I thought this would be a bit more interesting to talk about. So, innovation for reinforcement on the Unit 1 pond outfall building. What I'm going to be talking about is how we built the raft foundation of this building. That was between September 2020, about 8 months, so through to May 2021. But the nice thing about it, this piece of work, is actually a lot of the methods and the technologies we used were trialed there for the first time, and they're now being used on some of the adjacent structures, particularly the volutes in HPX. So everyone here will know the site very well. Real quick reminder for maybe perhaps some of the people online who don't. Pond outfall building is in the heat sink scope, up in blue at the top. And the purpose of the building, it regulates the pressure of various seawater cooling systems and then diverts all of the hot water back out into the Severn estuary. So yeah, the raft pour for this was 5,500 cubic meters. We did it in 2 pours across 3 levels. And just to point out a couple of the key features that had a bit of an impact on how we built this. In the middle of the lower port, in the middle of the basin to the north, is the outfall shaft. That's where all the hot water goes to get into the outfall tunnel. Got a lot of starter bars, so some of these are for internal walls. The radial wall around the outside was a particular challenge. And then there's also two large weirs, so some angled starter bars that have some slightly different tolerances to the normal vertical ones. And then around the outside, there's also a toe, and that's the mobilization of downward forces under seismic loading. So what made this raft so hard to build? There's essentially two key challenges we had. The first is that whilst lots of the geometry we saw on the previous slide was circular, it was semicircular, all of the reinforcement was not, it was still orthogonal. What that means in practice is all of the L bars round the edge of the raft, so bottom right, and all of the Z bars on the top mat, practically every single one of those bars has its own unique bar mark, its own unique geometry. We had pushing 2,300 individual bar marks on just the first raft bore. So that was a huge challenge. Then the next problem was just the sheer amount of the stuff. So top and bottom mat, 6 layers each, all 40 mil diameter for the most part, which is the maximum allowable. What that contributes to is average reinforcement density, 285 kilograms a cubic meter. Outside of nuclear, on normal building jobs, you'd be probably looking at about 90 to 130. As a result of, sort of the size of the pore, 5,500 cubic meters, and the density of it, with 52,000 bars, give or take, to install. So a lot of what I'm going to be talking about is how we broke that down into something a bit more manageable. So our reinforcement team actually did some quite cool work here with the digital team. When we get given a reinforcement model, we get some metadata, but our reinforcement team decided that actually it would be useful to have a bit more information in this model. So in red there, the T1Z, that's the layer name, so it's the top one layer, Z bars. And then, our reinforcement team actually broke that down into every single bundle that was going to be delivered. They decided what bar they wanted in what bundle. And then the bar ID in green, every single bar in every single bundle, they gave a letter of the alphabet to. And what they were aiming to do there is, if you want to find any given bar coming in on a trailer, you should know exactly what bundle it's in. You should know exactly what trailer, what bundle is on. In practice, I'd say it worked pretty well. The amount of time searching for bars went down hugely. Did have a couple of teething issues with bars getting ripped off in transit. Those have all now pretty much been resolved. They're doing and having no problems at all finding bars. So that one helped us hugely. Another thing we looked at as a team was we actually looked at how we're going to sequence building this raft. Traditionally, how you build this, you build your bottom mat, you then have your shear reinforcement and your support steel going concurrently, you build the top mat, and then the very last thing you do is you drop your starter bars down through the top mat, and you hope that there's a gap where you need a gap to get your starter bars in. That worried us a little bit. We just didn't trust that at all, particularly with the radial wall, where you've got a semicircular shape and square gaps. If it goes wrong, you've got issues with covers, you might struggle to get your plates in because you've had to move some of the bars, wall junctions aren't going to work. So we completely rehashed the build sequence. We built the bottom mat. We then did the starter bars at the same time as the support steel and the shear reinforcement. So you can see, step 2 there, that's freestanding starter bars as prefabricated units. We'll get onto that in a little bit. Top mat goes in last, and what that does, it gives positional priority to the starter bars, which, affects everything all the way up the building. to try and get the tonnage outputs we were looking for, the tons per man hour, we hugely pushed prefabrication during this build. So on the left, that's the bottom mat going in, and for the keen-eyed amongst you, you'll see some rectangular shapes down there. Those are mega mats, which I imagine a lot of you've seen. It's 10 to 15 parallel bars with some perpendicular lifting bars, and it means you can place 10 to 15 bars in one go. As Will would say there, when it's not windy, that is the only issue with it. But we also started looking at trying to do our vertical elements as prefabricated units. So that's a linear prefab cage for starter bars. And you can see in that picture there, it's going in before the top mat. And we did that pretty much all of the raft edges and all of the internal walls, bar a few tricky bits. And we pushed that further because we didn't just do the linear elements, we did the radial element surrounding the northern basin as well. Again, we were really concerned about getting the bars exactly where we wanted them here. So we decided to experiment with some templating. So these templates, we plasma cut them up in our on-site fabrication workshop. So we had a lot of help from the digital team modeling these around existing reinforcement. We had to make some temporary works decisions on how big the units were going to be, what could the crane lift, how far away is it, how big's the sheet of steel we can get into the plasma cutter, how big's our lifting beam, how curved is our lifting beam, what can we get on there. So we did this big exercise, and the idea was that we wanted to be able to lift the whole thing in a couple of days. So this is what it looks like in practice. We got everything cut, we gave it to the prefabricated reinforcement team. They assembled these prefabricated units, they welded the templates to them, and in the end we were able to lift in 141 linear meters of radial wall in 40 lifts over 2 days with very, very minimal setting out. If you look at the middle image there, there's no point planning everything perfectly and then putting it in the wrong order. So we stencil cut domino style numbers just to check that everything was where it was supposed to be. And then we also cut 13mm holes into every single template, and those can house a Leica mini prism. And what that means is our setting out surveying engineers, 4 measurements, you can check the exact position of 18 bars. And then, yeah, we have the lifting process to the far right. That shows one of the units going in. Moving forwards, this worked pretty well. We did learn some lessons. I think the next time that I'm aware of this being used is going to be the HPX aircraft protection shell. They're going to be doing something very similar. The last thing I'd like to talk about for how we broke this pour down into a manageable task is we use Trimble Connect. So I know that Frankie touched on this earlier. Some of the things we did at the time were a bit of a first, but for those of you who don't know the system well, it's model navigation software that you can use on a tablet computer at the coal face in real time. And one of the great features is actually, if you look at the bottom there, it's probably a bit small for this screen. You can set up all of the views in advance for the engineers, for the steel fixers who are building. So we actually did this, every single bit of prefabricated reinforcement we set up a view for, and you can even mark the measurements on it in advance. And what that means is you can send someone out with very little setting out training. You can give them a tape measure and you can say, please check all of the bar spacings. The other thing you can do with this is you can click on practically any bar. It'll give you the dimensions, the coupler status, the shape code, pretty much any kind of stat you need for that bar to check that it's right. We pushed it further though. So this raft bore was so complex that just the first bore had 86 drawings. Traditionally, how you do the QA for that is you'd mark up every single drawing you'd include it with the ITP. If you want an office copy as well as a site copy, because stuff gets lost, stuff gets damaged, 172 drawings. Quite frankly, none of us wanted to do that. So we used Trimble Connect statusing tools I believe quite a lot of work was done on this before I even got there by the digital team. And essentially, it's just a traffic light system. So the bars in grey there that are shown, those are bars that no one's looked at yet. Perhaps because they haven't been placed, or perhaps no one's got around to it yet. Bars in green, green's for good. Someone's checked those, someone's really happy with them. Yellow is bars that are going to require some further checking. Maybe we're not quite sure, maybe someone needs to ask a few questions about it. And then bars in red are bars that need further work to be installed in accordance with the works information. The fantastic thing about doing all of this digitally is obviously that gives you data that you can then work with. So one of the experiments we did was, instead of using the digital model to try and highlight bars to get their mass, or maybe having a really poorly organized spreadsheet, what we want to know is how many tons are we installing a week for productivity purposes, so we can adjust our program so that we can plan to have the right amount of labor. We were actually able to download all of our tonnages from a data warehouse. It was pretty accurate. So we found that it was plus minus a ton, which sounds pretty bad, but then we had 1,000 tons of reinforcement in this course. So what that actually means is 99.9% accurate. When I left this, there was some ongoing work to try and get that even more accurate. I would like to see where that goes. And then the last thing I'm going to touch on, just because it's related to the Trimble Connect items that we're talking about, is you can do a lot more than rebar with it. So we also had quite a lot of temporary works, quite a lot of form work that we wanted to manage. And the problem normally with managing these works is you give your carpenter a drawing and then, it gets lost, it gets damaged, it gets rained on, it gets superseded, and you can't really control that information. You've given it out, and unless you run around site looking for that dated drawing, the information's out of your hands. Benefit of issuing all of your drawings digitally is that you can control the information at any given one time. So these are all panel drawings for our carpenters that I issued. And whenever there's a design update, you update it on a tablet. And then unless someone's trying really, really hard, they can't access outdated information, even if they want to. So to summarize, we had quite a lot of challenges to contend with on this build. The complexity of the reinforcement and the density was like nothing I'd ever seen elsewhere on site. I'm sure somewhere there is something this complex. The non-linear geometry, particularly around the radial wall, was a big challenge for us. And just the sheer information volume, as I said earlier, 52,000 bars to be installed. And it's a nuclear project. We need to make sure that every single one goes in right. How do we do that? The solutions we found, we really leveraged digital technology with the help of the digital team. We challenged conventional wisdom. Why are we building the raft in this order? Is it because it's the best way to do it, or is it because it's the way we've always done it? And then detailed front-end engineering. So we've got a huge amount of knowledge in our temporary works team, in our methods teams, in our design management teams. Let's bring all of those people to the table to interrogate the design and to try and guess what the issues are before we encounter them on site. Thank you.
Conscious of time, I suggest we hand straight over to Amine to the last section. If there's any questions on the construction bit.
Thank you, Will. Very interesting.
Yes. Huge lag. Right, so patience.
I'm Amine. I'm one of the section engineers in the HL buildings, and we'll be talking about the AG installation. Can anyone tell me what AG stands for? Yeah.
Questions.
It's an auxiliary steam generator. So it's the emergency feed water tanks for the cooling system of the generators. There are 4 tanks in each nuclear island, which are located in the safeguard building, HL1, HL2, 3, and 4. Some numbers about the tanks, dimensions, they're 8.2 by 6.4 by 8.6 meters, which gives it 450 meter cube volume, which is the equivalent of 450,000 liters of water. It's a 90-ton lift, which is an interesting lift in any other site, not in HPC, which is another lift. 408 member studs and 208 shear connectors, which needed to be declashed in HL2 and 3. And the stainless steel panels travel 700 miles by boat to be constructed on site. Next is the planning and preparation. So just for this section of the HL buildings, the plan and method statement started 5 years prior installing, which in May 2016. The sliding scheme was divided by on site method teams between 2020 and 21. The formwork construction started in January 2021 for the first tank, ASG1, and the final tank, ASG3, was installed in September 21. So ASG1 and 4, they're located in the east and west of the generator. You can see it be lifted by a big car straight from the bunker to the final position. Just use small timber guides to ensure the installation was within the tolerances required. The donut method, which is basically just working all the adjacent elements and leaving a hole in the middle for the tank to be lifted in position afterwards. For the AG2 and 3, they're actually placed together in the center of the buildings. They're poured into 2 lifts with a double height wall of 8.7 meter height. And the former used was very complex due to the complexity of the elements. So it required 2 different systems, special statical formwork internally, and a combination of both original and pairing formwork from the external of the tanks. The rate of rise as well needed to be very low. So in this situation, it was 0.4 meters per hour, and this is due of the complexity of the patterns and the tank.
So just check the screen share. There's been a message from the group about saying
it says
It's going from your computer to that computer, isn't it?
yeah, it's sharing online. You say that, okay, cool.
So next is sliding of the tanks, the sequencing. If we take AG3 as an example, the first step is to slide in on a rail to allow reinforcement to be fixed on the central wall. Then this was one of the main challenges that we had as a team, which is declashing with the AG2 tank and with the wall rebar. So we extensive surveys needed to be done. As was mentioned before, we do the designers, they provide us with reports for declashing, but we have to do our own declashing on site because they cannot take into consideration all the tolerances and all the variations on site. Next is jacking the tank and loading on the rollers with the help of a big car, and then the tank needs to be pulled using chain blocks into the final position. It had to be slid 20 mil high at one end to avoid the clashes. And the final step was leveling the tank. So the lesson learned from this activity. They are for the great benefit of Unit 2, obviously. And the learning report was published on this activity with the main lessons can be highlighted here, which is a change of the rebar design from female couplers to male couplers for Unit 2, and this will allow the installation of the tank without having to tilt it. The second one is a change in the concrete mix design for the sliding plinth to a stronger design, which means we will reach the required strength quicker. This will give us more time for the tank construction, and obviously it will help to achieve greater accuracy. And the final point is to assemble the stainless steel liner into the frame before lifting it into position. This will allow us to not be to eliminate the risk of not reaching the tolerances needed for the concrete surface, for example, especially on the inside of the AEG, which is very minimal. It's 0 and -3 mil. So if we assemble it prior to lifting it, we won't have to worry about this point. Any questions?
We have a hand raised, Mr. Kelpie. Do you have something to say?
Yeah, just the screen share. Failed for those.
Say again, Mike, we lost you.
Well, we got no slides online.
You have no slides?
Not online.
It's up for a few.
Oh, right, okay. Are we good now, Mike?
No.
No, okay. Where are we in the presentation? Have we got another presenter? Okay, as soon as we're finished, Mike, rather than waste any time trying to fix
Oh, yeah, no worries.
Okay. Back to Andrew.
Was only if there are any questions? For either of the last two, I guess.
Difference of the density between 1 and 2, so that only made a difference for the curing time. It wasn't any other area that so you had a lesson learned on it.
Is that about the concrete mix?
Yes.
Yes, just for the current time, so we can continue with the other sequence of work in a short amount of time.
What was the difference? What was the difference? Yeah, the day, was it days? Because normally it's X amount of time to cure. What's the differential?
Normally, with concrete, it starts from C28 all the way to C60 in a nuclear site. If you increase it from, for example, from C28 to C40, you will have a 7-day roughly difference to reach.
Yeah, most of our concretes are reaching a week in the order of, depending on the time of year, a week or two.
That's great.
It's probably a fairly rare application where for that temporary condition we need pretty much the full strength.
7 days can make a huge difference.
Oh, yes. Thank you very much.
I sort of had a question over there. Did the Trimville Connect status tool?
Yes.
Use that to make sure that all these millions of bars are all going into the right place and it's all green all the way.
So on my scope, we did it for all 52,000 bars. Yes, I'd say it particularly lends itself to the bigger, larger, complex elements where it's quite easy to miss a bar. So we did it on the rafts. I think the team have gone back now to using some drawings on the walls, which are much smaller. That's a lot more.
So it's not used across site, it's more
it's used widely across site, but I think that was one of the few applications at the time where it had been used exclusively.
I guess we
pretty much chucked the drawings in the bin.
We have a range of different tools for different applications, but probably for two reasons. One is, the reality is we've been doing this at some scale for 5 years now, and the tools have developed quite a lot in that time, and things have evolved, and we're trying to strike a balance between having a consistent approach, but then giving the teams the opportunity to innovate. And then also the reality is we've got such a range of different work. Rob says the teams are doing fundamentally different things, and different tools are better for different jobs. In the prefabrication area, for example, where we prefabricate some of the cages that we were talking about, we use a completely different tool again, because it's just more targeted for that work.
there any further questions from people dialing in? Take the chance now, please. Deafened by silence. Okay, thank you very much, Andrew, for yourself and your team. A round of applause, please. I'd like to say well done. Thoroughly enjoyed each of your presenters. And I did learn a lot today. Considering I've been on the job for 6 years, that did surprise me, but I have learned. Very good. I'm sure everybody else did as well. We certainly saw different aspects, because we may know a lot about our particular islands, but your spread covered all of the islands, which is really good. The duration of the talk took us over an hour, so I'm willing to say thank you very much. And what I'll do is I'll offer 2 hours of CPD, John, quietly. Wink, wink. Anyway, I'm just going to say thank you very much for presenting. Thank you very much. Mike, do we have any idea who may be presenting for us next month?
No, but there's a few. Well, there's 2 people who may be interested in doing it, and when I get back next week, I'll be having a chat to those people and see who wants to do the first one.
Perfect, Mike. I have every faith in you. Thank you very much. Before I close the meeting, I'm just going to go around the table and online. Any other business? It's amazing.
Just a quick, Scotty.
We'll take them. Who's that? Mike? Was that you?
Scotty. Yeah, I'll just, again, as CPD officer, just want to thank Andrew and his team, and thanks for giving us your precious time to prepare a talk. And I'm constantly humbled by the wonderful, dedicated, skilled people on this unique world-class project. I want to thank Central Engineering, not only for this fascinating insight into their world, but also for the vital, but often unsung work they do across the HPC site. Thank you all.
Thanks, Mike. I'm going to second that sentiment and ask Andrew, you're going to come back and present again for us in 6 months' time?
Sentence. Just say no.
It's a nice round time frame. 2 a year. I won't hold you to that. I'll let Mike sort that out. That's Mike's. Just always keen to get a plug where I can, because I was the lecturer and CPD secretary for a couple of years myself, so I know how hard Mike's job is trying to round people up. So, any other business online? Again, silence. I love screaming out for the people online, because I just don't know if there's ever going to be a response. We'll just sit here and just be waiting for somebody to turn their microphone. I'll take that as a no. With that, I'll close the meeting. The next meeting is the 4th Thursday of July, which is the 28th. I look forward to seeing you there. Andrew Jackson and the team, you're welcome to attend. You're always welcome. Hopefully you're getting the invitations. If you're not, please contact John Pym, who will be more than happy to put you all on the distribution list.
If there's anybody that didn't sign the sign-in papers, if you could just, perhaps Amine, did you arrive a little bit after it when we passed it? Yeah.
Thanks for a great evening, everyone.
Cheers, Mike. Thanks everybody online. See you next month.
Thank you. Bye.
Right.